Look up at the night sky. What you see is just a fraction of the grand puzzle. The stars, the galaxies, even the vast emptiness between them are part of something far bigger, something we still don't fully understand. What if everything we know about the universe's shape is just the tip of an unimaginable cosmic iceberg? Scientists have spent centuries trying to crack this mystery, and what they've discovered will bend your perception of reality. From flat expanses to twisted donut shapes, from holograms to hidden dimensions, the universe might not look anything like we've been taught. Today, we're diving into 30 mind-blowing theories about the true shape of everything that exists. Some will sound like science fiction, others might just rewrite the laws of physics as we know them. So buckle up, because by the end of this journey, you'll never see the cosmos the same way again. Now, let's start with one of the most widely accepted ideas in modern cosmology, the flat universe theory. Picture space as an endless sheet of paper, stretching out in all directions without any curves or bends. This is what scientists mean when they say the universe is flat. But how do we know? The key evidence comes from the cosmic microwave background radiation, the faint afterglow of the Big Bang. Precise measurements of this radiation show patterns that match perfectly with Euclidean geometry, the same flat geometry you learned about in math class. No warping, no hidden folds, just straightforward, infinite space. What's fascinating about this theory is what it implies for the future of the cosmos. A flat universe suggests it could expand forever, growing colder and more spread out over trillions of years. This idea fits neatly with the lambda-CDM model, the leading framework in cosmology that combines dark energy and cold dark matter to explain how the universe evolves. If the universe truly is flat, then the mysteries of dark energy and dark matter become even more crucial to unlocking the ultimate fate of everything we see. So while it might sound simple at first, the flat universe theory opens up some of the biggest questions in science. Now, let's take a step into a completely different cosmic landscape, the spherical universe theory. Imagine space not as a flat sheet but as the surface of a giant balloon. In this model, the universe curves back on itself, forming a closed, finite shape. If you could travel far enough in one direction, you'd eventually loop back to where you started, just like sailing around the Earth. This idea isn't just science fiction. It's rooted in Einstein's theory of general relativity, which tells us that massive objects warp the fabric of space-time. A spherical universe would have some mind-bending consequences. For starters, it would mean the cosmos has a finite volume, unlike the endless expanse of a flat universe. Picture living inside a bubble where every direction eventually leads you home. But how would we know if this is true? Scientists look for subtle clues in the cosmic microwave background, searching for patterns that suggest space is curved. So far, the evidence points toward flatness, but the spherical model remains a fascinating possibility. What's really intriguing is how this theory challenges our intuition about space. In a spherical universe, parallel lines wouldn't stay parallel forever. They'd eventually meet, and triangles would add up to more than 180 degrees. It's a reminder that the cosmos might not play by the rules we learned in school. Whether the universe is flat, spherical, or something even stranger, each theory pushes us to rethink our place in the grand scheme of things. Now let's shift gears and explore a universe that bends the rules of geometry, the Hyperbolic Universe. Picture space not as flat or spherical, but shaped like a saddle, curving away from itself in what scientists call negative curvature. In this wild cosmic landscape, parallel lines don't just diverge, they spread apart dramatically, and triangles add up to less than 180 degrees. It's as if the universe itself is stretching everything apart at an accelerating pace. This saddle-shaped model isn't just a mathematical curiosity, it has real implications for how the cosmos behaves. A hyperbolic universe would expand faster than flat or spherical ones, with galaxies drifting apart more rapidly over time. Imagine blowing up a balloon with tiny dots on it, but instead of the dots moving apart at a steady rate, they fly away from each other as if pushed by an invisible force. That's the kind of expansion we're talking about here. What's even stranger are the geometric quirks. In a hyperbolic universe, the farther you travel, the more space seems to warp. Distant galaxies would appear smaller and more crowded than they actually are, like reflections in a funhouse mirror. Scientists test for this by studying the cosmic microwave background, looking for telltale signs of negative curvature. So far, the evidence still favors a flat universe, but the hyperbolic model reminds us just how bizarre and unpredictable the cosmos could be. Whether space is flat, spherical, or saddle-shaped, each theory challenges our understanding of reality in ways that keep astronomers and the rest of us on our toes. Now, let's take a cosmic detour into one of the most mind-bending shapes our universe might take, the toroidal universe. Imagine space not as an infinite plane or a curved sphere, but as a giant donut where every direction eventually loops back on itself. In this model, if you traveled far enough in a straight line, you'd end up right where you started, like walking around the surface of a ring without ever hitting an edge. It's a universe that's finite in size but has no boundaries, a cosmic Möbius strip where the rules of geometry get twisted in fascinating ways. This donut-shaped topology isn't just a quirky thought experiment. It could actually solve some puzzling mysteries in our observations of the cosmos. For instance, scientists have spotted strange anomalies in the cosmic microwave background, the afterglow of the Big Bang. Some of these irregularities, like unusually large cold spots or repeating patterns, might make more sense if space itself is twisted into a torus. Picture the CMB as a wallpaper pattern on this cosmic donut. Certain designs would repeat in predictable ways, giving us clues about the universe's true shape. What's even more intriguing is how a toroidal universe challenges our ideas of infinity. Unlike a flat or hyperbolic cosmos that stretches endlessly, a torus offers a finite space without walls or edges. You could think of it like a video game world where leaving one side teleports you to the opposite side. Everything is contained, yet unbounded. While current evidence still leans toward a flat universe, the toroidal model reminds us that the cosmos might be far more intricate than we've ever imagined. Whether space is a donut, a saddle, or something even stranger, each theory peels back another layer of the universe's deepest mysteries. Now, let's shift gears to something even more mind-bending: the holographic universe. What if everything we see, touch, and experience in 3 dimensions is actually a projection from a 2-dimensional surface? That's the core idea behind the holographic principle, a theory that turns our understanding of reality inside out. Imagine the universe as a cosmic movie screen, where the 3D world we live in is just a hologram projected from information encoded on a distant 2D boundary. It sounds like science fiction, but this idea comes straight from the cutting edge of physics, merging quantum mechanics and gravity in a way no other theory has managed. The holographic principle first gained traction through the study of black holes. When matter falls into a black hole, it doesn't just vanish. Its information gets smeared across the black hole's event horizon, the point of no return. This discovery led physicists to realize that all the information inside a black hole could be stored on its 2D surface, like data etched onto a cosmic hard drive. From there, the leap wasn't so far to suggest that our entire universe might work the same way. A 3D illusion built from 2D data. What makes this theory so powerful is how it bridges 2 of physics' biggest puzzles, gravity and quantum mechanics. Normally, these 2 frameworks don't play nice. Gravity describes the universe on cosmic scales, while quantum mechanics rules the tiny world of particles. But in a holographic universe, gravity in 3D space could emerge from quantum interactions on a 2D surface, like a shadow cast by a deeper reality. It's as if the universe is solving its own equations by simplifying them into fewer dimensions. While we don't have definitive proof yet, the holographic principle has already reshaped how scientists think about space, time, and information. If true, it would mean the universe is far stranger than we ever imagined, not just a stage for events, but a projection of something more fundamental. Whether it's black holes whispering secrets or the fabric of space-time itself encoding reality, this theory invites us to question what's real and what's just a cosmic illusion. Now, let's stretch our imaginations even further. What if our universe isn't alone? Picture a cosmic ocean where countless bubbles float, each one a self-contained universe with its own unique shape, laws, and even realities. This is the multiverse theory, a mind-blowing idea that suggests our universe is just one of many, perhaps even an infinite number, all existing side by side in a grand cosmic tapestry. The multiverse concept isn't just wild speculation, it emerges naturally from inflationary cosmology, the leading theory of the universe's explosive early expansion. According to this model, the rapid stretching of space during inflation didn't stop everywhere at once. Instead, it could have created pockets where inflation ended, forming bubble universes like ours, while other regions kept expanding endlessly. Over time, this process might have spawned an endless array of universes, each with its own distinct physics. Some might have stars and galaxies like ours, while others could be ruled by entirely different forces, with shapes and dimensions we can't even fathom. One striking version of this idea is the bubble multiverse, where each universe is like a separate bubble in an ever-growing cosmic foam. These bubbles don't pop, they drift apart, forever out of reach because the space between them expands faster than light. That means we'll never see or touch these other universes, but their existence could explain puzzling features of our own cosmos, like why the laws of physics seem so finely tuned for life. If there are infinite universes with random variations, it's no surprise that at least one got lucky. The multiverse theory doesn't just challenge our place in reality, it reshapes how we think about possibility itself. Could there be a universe where gravity pushes instead of pulls, where time runs backward, or where the cosmos is shaped like a vast, twisting knot? The multiverse suggests the answer might be yes. While we can't yet prove these alternate realities exist, the idea pushes the boundaries of science and philosophy, inviting us to wonder just how big and how strange existence truly is. Now let's turn our attention to a theory that suggests the universe might not have a single beginning or end. Instead, it could be caught in an eternal loop. Imagine a cosmic heartbeat where the universe expands, contracts, and then starts all over again in an endless cycle. This is the Cyclic Universe model, a fascinating alternative to the traditional Big Bang narrative. In this scenario, what we call the Big Bang wasn't the absolute beginning but just one phase in an infinite series. Picture a universe that expands until gravity finally pulls everything back together in a big crunch. But instead of vanishing into nothingness, that collapse could trigger another Big Bang, birthing a fresh universe with new possibilities. This cycle could repeat indefinitely, with each iteration leaving subtle traces in the cosmos, clues that might one day help us uncover the truth. The cyclic model doesn't just rewrite the universe's origin story, it also reshapes our view of its fate. Unlike theories where the cosmos expands forever into cold darkness or collapses into a singularity, this idea offers a middle ground. It suggests that destruction isn't the end but a prelude to rebirth, with each cycle potentially tweaking the laws of physics, creating slight variations in each new universe. Some versions of this theory, like Roger Penrose's conformal cyclic cosmology, propose that black holes from one era could seed the next, carrying forward information in ways we don't yet understand. Others suggest that dark energy, the mysterious force driving the universe's acceleration, might eventually reverse its role, pulling everything back together. While evidence for the cyclic universe remains speculative, it challenges us to rethink time itself, not as a straight line but as a vast, unending spiral of cosmic renewal. What's truly mind-bending is the possibility that our universe isn't the first or the last in this grand cycle. Could remnants of a previous cosmos be hidden in the cosmic microwave background? Or might gravitational waves hold echoes of a universe that existed before ours? The cyclic model keeps these questions alive, reminding us that the cosmos might be far more dynamic and far stranger than we ever imagined. Now, let's step into a theory that takes the cosmic mystery to another dimension literally. Picture our universe not as an isolated three-dimensional space, but as a vast floating membrane or brane drifting in a higher dimensional realm. This is the Brane World Scenario, a mind-bending idea that emerges from the depths of string theory. In this model, our entire universe could be just one of many branes existing in a higher dimensional space called the bulk. Think of it like a slice of bread in a cosmic loaf, except this slice contains everything we know: galaxies, stars, even us. But here's where it gets wild. While particles like light and matter are trapped on our brane, gravity might be the only force that can leak into the bulk, spreading its influence across extra dimensions. This could explain why gravity feels so weak compared to other forces. It's not confined to our brane like everything else. String theory plays a starring role here, suggesting that these extra dimensions aren't just mathematical quirks but real physical spaces. Some versions of the Brane world idea propose that collisions between branes could even trigger events like the Big Bang, resetting the universe in a cataclysmic clash of higher dimensional membranes. Others hint that dark matter might be ordinary matter trapped on a neighboring brane, invisible to us but exerting gravitational pull from afar. While the Brane World Scenario remains speculative, it opens doors to radical possibilities. Could there be parallel universes just a millimeter away in an unseen dimension? Might gravity's peculiar behavior hold the key to detecting these hidden realms? For now, these questions linger at the edge of science, challenging us to rethink not just the shape of the universe, but the very fabric of reality itself. Now, let's unravel a theory that paints the cosmos in a mesmerizing, almost artistic light: the fractal universe. Imagine the universe not as a smooth, uniform expanse, but as an intricate tapestry where patterns repeat themselves endlessly, from the smallest scales to the largest. This is the fractal hypothesis, a striking idea that suggests the cosmos might mirror the self-similar structures found in nature, like snowflakes or coastlines. At its core, a fractal is a shape that looks the same no matter how far you zoom in or out. Apply that to the universe, and you get a mind-bending possibility: galaxies clustering in ways that echo the distribution of stars within them, or cosmic voids repeating like bubbles in a foam. Some researchers point to the way galaxies are scattered across the sky, noting how their arrangements seem to follow a fractal-like pattern, at least up to certain scales. Even the vast, empty regions between galaxies, known as cosmic voids, appear to repeat in a way that hints at this recursive design. But here's where it gets controversial. While some observations support the fractal idea, others clash with the standard model of cosmology, which assumes the universe becomes smooth and uniform at the largest scales. Proponents of the fractal universe argue that our current tools might just be missing the bigger picture literally. If the fractal pattern holds true, it could mean the universe has no real edge or average density, just an endless repetition of structure. Could the universe truly be a fractal, a cosmic echo of itself on every scale? Or is this just a fleeting illusion in the data? For now, the fractal universe remains a tantalizing what if, challenging us to see the cosmos not as a blank canvas, but as an infinite, swirling masterpiece of patterns. And with that, we're ready to twist our perspective even further, because next, we're diving into a universe shaped by torsion and spin. Now, let's take a cosmic detour into a universe where space-time itself isn't just curved, it's twisted. This is the Einstein-Cartan universe, a theory that reimagines the fabric of reality with a radical twist, literally. While Einstein's general relativity describes gravity as the bending of space-time, the Einstein-Cartan theory goes a step further, introducing a property called torsion. Picture space-time not as a smooth rubber sheet but as a coiled spring, where every twist and turn could reshape the cosmos in ways we're only beginning to understand. So, what exactly is torsion? In simple terms, it's the idea that space-time doesn't just curve, it also spins like a corkscrew threading through the universe. This spin isn't just a quirky detail, it could explain some of the biggest mysteries in physics. For instance, torsion might give the universe a helical or spiral-like shape on the grandest scales, a far cry from the flat or spherical models we've explored earlier. Imagine galaxies not just drifting apart but swirling along invisible twisted pathways, like leaves caught in a cosmic whirlpool. But the real magic of this theory lies in its potential to solve puzzles like dark matter and singularities. Some researchers suggest that torsion could mimic the effects of dark matter, explaining why galaxies rotate faster than expected without invoking invisible particles. Instead, the twisted geometry of spacetime itself might be creating the extra gravitational pull we observe. And when it comes to black holes, torsion could soften their infamous singularities, those infinitely dense points at their cores, replacing them with smoother, more physical structures. Of course, the Einstein-Cartan universe isn't without its skeptics. Detecting torsion directly is a monumental challenge, and the math behind it is notoriously complex. Yet, it offers a thrilling alternative to mainstream cosmology, one where the universe isn't just warped but dynamically, elegantly twisted. Could this be the missing piece in our cosmic puzzle? For now, it's a compelling reminder that spacetime might be far more intricate and far more alive than we ever imagined. And with that, we're ready to step into even stranger territory, because next we'll explore a universe where the laws of physics might be flipped entirely. Now, let's turn the universe inside out, because what if everything we know has a perfect opposite? Welcome to the Mirror Universe, a mind-bending theory where the laws of physics aren't just different, they're flipped. Imagine a cosmos where left becomes right, positive charges turn negative, and time might even flow backward. This isn't science fiction, it's a serious hypothesis rooted in the quirks of quantum symmetry. At the heart of this idea is something called parity symmetry, the notion that the universe should behave the same way if you flip it like a mirror image. But here's the twist. In the 1950s, physicists discovered that certain particles violate this symmetry, preferring one direction over another. This breakthrough led to a wild question. What if that broken symmetry created an entire shadow universe, identical to ours but with everything inverted? One way this could happen is through a phenomenon known as spontaneous symmetry breaking in quantum fields. Picture a cosmic coin toss at the dawn of time. Our universe landed on heads, while the mirror universe landed on tails, locking in opposite physical laws. The result, a hidden twin cosmos where atoms twist the other way, forces repel instead of attract, and even the arrow of time could point in reverse. But how would we ever detect such a universe? Some scientists speculate that gravitational waves or subtle anomalies in cosmic radiation might carry hints of mirror matter interacting with ours. Others suggest that certain particles, like neutrinos, could act as messengers between the two realms. And if the mirror universe exists, it might even explain mysteries like dark matter. What if it's just ordinary matter from the other side, invisible to us except through gravity? Of course, the mirror universe remains speculative with no direct evidence yet, but it challenges us to think bigger, to consider that reality might be far stranger than a single cosmos with fixed rules. Whether it's out there or not, this theory reminds us that the universe loves symmetry, and sometimes breaking it leads to the most fascinating possibilities. And speaking of breaking norms, our next stop takes us into a universe where the Big Bang might not be the beginning, but a rebirth. But what if the universe itself is hiding inside something even more mysterious? Let's step into a theory that turns cosmic origins upside down: the black hole universe. Picture this: our entire cosmos might not just contain black holes, but actually be one, nestled inside a much larger parent universe. Here's how it works. When a star collapses into a black hole, it doesn't just vanish, it forms an incredibly dense point called a singularity, where space and time break down. Now, imagine that singularity doesn't just sit there. Instead, it births an entirely new universe inside it, with its own space-time laws and even another Big Bang. That's the core of this mind-bending idea. Our universe could be the interior of a black hole from another reality. This theory offers a radical twist on the Big Bang. Instead of a one-time explosion from nothing, the birth of our universe might have been the moment a black hole formed in another cosmos, creating a bridge between realities. The intense gravitational squeeze of that collapse could have sparked everything we see today. And here's the kicker: it might solve one of physics' biggest puzzles, the nature of singularities. Inside a black hole, the rules of Einstein's relativity crumble. But if that singularity is actually the seed of a new universe, it could explain why we'll never observe one directly. Some physicists take this further, suggesting that every black hole in our universe might contain its own baby cosmos, spawning an endless fractal of realities. It's a dizzying thought that the night sky's black holes could each be doorways to other worlds, with their own stars, galaxies, and maybe even life. Of course, this idea isn't without challenges. We can't peer inside a black hole to test it, and the math gets murky at the extremes. But it's a powerful reminder that the universe might not just have mysteries, it might be one. And if we're living inside a black hole, who's to say what's outside? Perhaps another universe, nested like a cosmic Russian doll, waiting to be discovered. Now let's shift gears to a theory that rewrites time itself, where the universe doesn't just expand and collapse, but cycles endlessly like a phoenix rising from its own ashes. But what if the Big Bang wasn't the beginning at all? Let's explore a theory that stretches time itself: Roger Penrose's conformal cyclic cosmology. This idea flips the script on cosmic origins, proposing that our universe is just one chapter in an endless cycle of rebirth. Here's the twist: instead of a single explosive beginning, Penrose suggests that universes repeat in an infinite loop, each one giving rise to the next through a process called conformal rescaling. Imagine the universe as it expands and fades over trillions of years, eventually becoming so vast and empty that all matter decays into pure energy. At this point, space and time lose their meaning, distances and durations stretch into infinity, but mathematically they can be rescaled to zero. In this strange state, the end of one universe becomes the smooth, seamless start of another, with no singularity or Big Bang required. This challenges everything we thought we knew. The traditional Big Bang model paints a fiery beginning, but Penrose's theory erases that boundary entirely. There's no starting point, just an eternal sequence of universes, each inheriting faint echoes from the one before. Remarkably, Penrose and his colleagues claim to have found evidence of these echoes in the cosmic microwave background, patterns they call Hawking points, possibly remnants of black holes from a previous cosmic cycle. Critics argue that the math is speculative and the idea of infinite cycles is hard to test. But if Penrose is right, our universe isn't just expanding, it's part of an unbroken chain, stretching backward and forward forever. No beginning, no end, just an endless dance of creation and transformation. And that raises a haunting question. If time is truly cyclical, how many times has this story already been told? Now, let's turn to a theory that takes us back to the early days of cosmology, a vision of the universe that once ruled the textbooks before Hubble changed everything. Before we dive into the next mind-bending idea, let's take a step back, way back. to a time when scientists believed the universe was eternal and unchanging. This brings us to the static universe model, a theory that once dominated cosmology before Edwin Hubble turned everything upside down. Picture a cosmos that never grows, never shrinks, just exists exactly as it is forever. That was the static universe, a timeless, infinite space where stars and galaxies might move, but the big picture stayed the same. This idea made perfect sense to early astronomers. After all, if you looked at the night sky 100 years ago or 1,000, it would have seemed just as vast and unchanging. Even Einstein was convinced, tweaking his equations of general relativity to include a cosmological constant to keep the universe static, a move he later called his greatest blunder. But then came Hubble's bombshell discovery in the 1920s. By observing distant galaxies, he noticed something shocking. They were all racing away from us. The universe wasn't static at all, it was expanding. This shattered the old model and laid the groundwork for the Big Bang theory we know today. So why even talk about the static universe now? Because it's a fascinating what if. Some modified versions still linger in the fringes of cosmology, like the steady-state theory, which tried to salvage the idea of an unchanging cosmos by suggesting new matter is constantly created to fill the gaps as space expands. Others wonder if dark energy's mysterious push could someday balance the universe back into a near-static state in the far, far future. The static universe may have been debunked, but it's a reminder of how science evolves. What seems unshakable today might be overturned tomorrow. And that's what makes cosmology so thrilling. Now, let's shift gears to a theory that takes expansion to the extreme. A universe where dark energy doesn't just push, it dominates completely. Now, let's turn our attention to a universe that never stops stretching, the De Sitter universe. Named after Dutch astronomer Willem de Sitter, this model describes a cosmos where dark energy isn't just a player, it's the star of the show, driving an exponential expansion that grows faster and faster over time. Imagine space itself stretching at an ever-increasing rate, like a balloon inflating so quickly that distant galaxies vanish over the cosmic horizon, leaving us in an isolated pocket of reality. That's the De Sitter universe in action. Unlike the static model we just discussed, this one is anything but unchanging. In fact, it's the exact opposite, a runaway expansion where dark energy's repulsive force overwhelms gravity, pushing everything apart until even the fabric of spacetime is stretched thin. This idea isn't just theoretical. It plays a starring role in our understanding of cosmic inflation, the rapid expansion thought to have occurred in the first fractions of a second after the Big Bang. Many scientists believe the early universe behaved like a De Sitter space, ballooning exponentially before settling into the slower expansion we see today. But the De Sitter model isn't just about the past, it might also be the key to our far future. If dark energy continues to dominate, our universe could eventually evolve into a near-perfect De Sitter state. Picture a cold, empty cosmos where galaxies are so far apart that their light can never reach us, and new stars stop forming entirely. It's a lonely fate, but one that aligns eerily well with current observations of accelerating expansion. What makes this theory so compelling is how it bridges the earliest moments of the universe with its ultimate destiny. Whether describing inflation or the long-term effects of dark energy, the De Sitter universe offers a stark vision, one where expansion isn't just a phase but the defining feature of reality itself. Now, let's flip the script and explore a universe with the opposite curvature, the anti-De Sitter universe. While the De Sitter model stretches endlessly under dark energy's influence, anti-De Sitter space bends inward, creating a negatively curved cosmos where parallel lines eventually diverge. Picture the surface of a saddle stretching infinitely in all directions, but with gravity so strong that it pulls space itself into a warped, hyperbolic shape. This isn't just a mathematical curiosity. Anti-De Sitter space plays a starring role in string theory and the holographic principle. In fact, it's the backbone of one of the most groundbreaking ideas in modern physics, the AD/CFT correspondence. This theory suggests that a higher dimensional anti-de Sitter universe could be mathematically equivalent to a lower dimensional quantum field theory on its boundary. In simpler terms, it's like the entire 3D universe we experience might be encoded on a 2D surface, much like a hologram. But here's the catch: while anti-de Sitter space is a theorist's dream, offering elegant equations and profound insights into quantum gravity, it doesn't quite match the universe we observe. Our cosmos appears to be dominated by dark energy, pushing it toward de Sitter-like expansion, not the inward curvature of anti-de Sitter. That disconnect makes this model more of a playground for theoretical breakthroughs than a direct description of reality. Still, the anti-de Sitter universe remains a vital tool. It helps physicists untangle the knots between gravity and quantum mechanics, offering clues about black holes, space-time singularities, and the very nature of information in the cosmos. So while we might not live in an anti-de Sitter space, studying it could be the key to unlocking deeper truths about the universe we do inhabit. Now, let's shift gears to a theory that turns the Big Bang on its head: the Hyperbolic Universe. Instead of a single explosive beginning, this model suggests our cosmos was born from a dramatic collision between two higher dimensional membranes, or branes, floating in a vast, unseen bulk space. Picture two sheets of paper smashing together in a higher dimensional realm, releasing enough energy to spark the universe as we know it. This idea isn't just a wild thought experiment, it's a serious alternative to cosmic inflation. While inflation proposes a rapid expansion of space to explain why the universe looks so uniform, the Hyperbolic scenario argues that a slow, grinding collision between branes could have smoothed out the cosmos just as effectively. Imagine kneading dough until every lump disappears. That's how these colliding branes might have erased irregularities, leaving behind the remarkably even universe we observe today. But here's where it gets even more intriguing. Unlike inflation, which relies on a mysterious inflated field, the Hyperbolic model ties everything to the physics of branes and extra dimensions, concepts straight out of string theory. It suggests that the Big Bang wasn't the absolute beginning, but just one chapter in an endless cycle of collisions and rebirths. Each smash could spawn a new universe, meaning ours might be one in an infinite series. Of course, this theory isn't without its challenges. Detecting evidence of brane collisions or higher dimensions is no easy feat, and some argue that the model struggles to explain certain features of the cosmic microwave background. Still, the Hyperbolic Universe offers a compelling twist on cosmology, blending string theory with the story of our origins. Whether it's the true shape of reality or just a stepping stone to deeper truths, it reminds us that the universe's history might be far stranger and more spectacular than we ever imagined. Now let's venture into one of the most mind-bending ideas yet: the hairy black hole universe. Forget the smooth, featureless black holes you've seen in textbooks. This theory suggests our entire cosmos might resemble a black hole with wild, intricate structures on its surface, like cosmic hair. Picture a black hole not as a simple void but as an object bristling with complex, dynamic features, and then imagine that on the scale of the universe itself. This idea challenges the classic no-hair theorem, which states that black holes can be described by just three properties: mass, spin, and charge. But quantum gravity, the quest to unite general relativity with quantum mechanics, hints that black holes might have far more going on. Tiny quantum fluctuations near the event horizon could create a frothy, chaotic surface, giving rise to what physicists call hair. If this is true for black holes, could the universe in some way mirror this bizarre structure? Some theories propose that the universe's large-scale geometry might carry similar quantum imprints, meaning the fabric of spacetime itself could have hidden textures or irregularities. These wouldn't be visible in everyday life, but they might leave subtle fingerprints in gravitational waves or the cosmic microwave background. It's a radical thought, our universe as a colossal, hairy black hole with its own quantum fuzziness etched into the very framework of reality. Of course, this remains speculative, and detecting such features would require breakthroughs in quantum gravity and cosmology. But the hairy black hole universe pushes us to rethink not just black holes but the nature of spacetime itself. Whether it's a fleeting hypothesis or a glimpse into a deeper truth, it's a reminder that the universe's shape might be far more intricate and far stranger than we ever imagined. Now let's unravel another fascinating layer of cosmic possibility, the quilted multiverse. Imagine the universe as an infinite patchwork of space, where every possible arrangement of matter and energy repeats itself over and over like an endless cosmic quilt. If space truly stretches on forever, then somewhere out there, there's another you reading these very words, or a version of Earth where history unfolded just slightly differently. This idea hinges on the concept of infinity. In an infinite universe, particles can only arrange themselves in so many ways before patterns start repeating. Quantum randomness ensures that, given enough space, identical regions will emerge purely by chance. It's like shuffling a deck of cards forever. Eventually, you'll get the same sequence twice. In the quilted multiverse, this means there could be countless copies of our observable universe, each with tiny variations or eerily perfect duplicates. But what does this mean for us philosophically? It's a dizzying thought. If every possible version of reality exists somewhere, it challenges our notions of uniqueness and free will. Are our choices truly ours if every outcome plays out in some distant patch of the multiverse? Some argue this idea renders life meaningless, while others find comfort in the thought that somewhere every mistake is undone and every opportunity is seized. Scientifically, the quilted multiverse is hard to test after all. These duplicate regions lie far beyond our observable horizon. Yet it forces us to grapple with profound questions about infinity, probability, and the nature of existence itself. Whether it's a cosmic reality or just a mind-bending thought experiment, the quilted multiverse reminds us that the universe, or universes, might be far stranger and more interconnected than we ever dreamed. Now, let's shift gears to one of the most debated ideas in modern cosmology, the simulated universe. What if everything around us, from the stars above to the screen you're watching right now, isn't real in the way we think? Instead, it could all be an incredibly advanced simulation crafted by a civilization with technology far beyond our own. This mind-bending concept, known as the simulation hypothesis, suggests that our universe's shape, and even its very fabric, might just be lines of code in a cosmic computer program. The argument for this theory starts with a simple question. If a civilization could create simulations indistinguishable from reality, wouldn't they eventually run countless versions of them? Over time, the number of simulated realities would vastly outnumber the base reality, making it statistically more likely that we're living in one of those simulations. Proponents point to oddities in quantum mechanics, like the way particles behave only when observed, as potential glitches or shortcuts in the code. Even the mathematical precision of the universe's laws could hint at an underlying programmed structure. But not everyone's convinced. Critics argue that the simulation hypothesis is untestable, a fun thought experiment, but not real science. If the simulation is flawless, how could we ever detect it? Others question why an advanced civilization would bother simulating something as mundane as everyday human life. And then there's the energy problem. Running a universe-sized simulation would require unimaginable computational power, raising doubts about its feasibility. Philosophically, the idea forces us to confront big questions. If we're just data in someone else's program, does free will exist? Are our struggles and triumphs just predetermined outputs? Some find the notion unsettling, while others see it as a strange comfort, a reminder that even if reality isn't real, our experiences still matter to us. Whether you find the simulation hypothesis plausible or far-fetched, it undeniably stretches our imagination. It challenges us to rethink not just the shape of the universe, but the very nature of existence. And in doing so, it proves that the boundaries between science, philosophy, and science fiction are often thinner than we think. Now, let's circle back to a shape that's as intriguing as it is delicious, the donut universe. You might remember we touched on the toroidal model earlier, but recent research has given this theory fresh momentum, especially when it comes to explaining some of the cosmos' most puzzling quirks. Imagine our universe not as an infinite plane or a sprawling sphere, but as a giant cosmic donut where space loops back on itself in all directions. This shape isn't just a mathematical curiosity. It could hold the key to mysteries like the infamous cold spot in the cosmic microwave background. The cold spot is one of those cosmic anomalies that keeps scientists up at night. It's a strangely frigid region in the afterglow of the Big Bang, far colder than standard models predict. While some theories chalk it up to a statistical fluke or a vast cosmic void, the toroidal universe offers a compelling alternative. If space is shaped like a donut, light traveling through it could take multiple paths, creating overlapping patterns in the cosmic microwave background. These overlaps might produce cold spots like echoes of the universe's structure imprinted on the sky. But the donut model isn't just about explaining anomalies, it also reshapes our understanding of the cosmos scale. In a toroidal universe, the size of space could be finite yet boundless, meaning you could theoretically travel in one direction and end up right back where you started. This idea isn't just science fiction, it's grounded in rigorous topology, the study of shapes and spaces. Recent simulations suggest that if the universe is toroidal, its circumference might be far smaller than we once thought, perhaps even within the observable horizon. That would mean the farthest galaxies we see could actually be mirror images of closer ones, glimpsed as light wraps around the donut's curves. Of course, the toroidal model isn't without its critics. Some argue that the donut shape would leave other, more obvious imprints on the cosmic microwave background, ones we haven't found yet. Others point out that a small, finite universe would clash with certain measurements of cosmic expansion. But proponents counter that our observations might simply be incomplete, or that the universe's topology is more complex than a simple donut with twists and folds we haven't mapped. What makes this theory so fascinating is how it bridges the abstract and the observable. It takes a shape we encounter every day, a humble donut, and scales it up to cosmic proportions, offering a fresh lens to decode the universe's deepest secrets. Whether the toroidal model holds up to future tests or not, it reminds us that sometimes the answers to the biggest questions might be hiding in plain sight, wrapped in the geometry of the familiar. Now, let's stretch our imaginations even further as we step into the mind-bending realm of string theory's landscape. This isn't just about one universe, it's about a staggering multiverse of possibilities, each with its own shape, rules, and even laws of physics. String theory, the framework that tries to unite quantum mechanics and gravity, suggests that the fabric of reality isn't limited to the universe we see. Instead, it could be one of countless others in a vast cosmic tapestry, each with a unique geometry and physical constants. Picture this: every possible shape for a universe, flat, spherical, hyperbolic, even twisted into higher dimensional knots, exists somewhere in this landscape. The reason we find ourselves in a universe with the precise conditions for life might come down to something called the anthropic principle. It's the idea that out of all possible universes, only those with the right constants, like the strength of gravity or the mass of electrons, could ever host observers like us. In other words, we're here because this particular universe's shape and rules allow it. But here's where it gets even wilder. String theory's landscape isn't just a static collection of universes. Some theories suggest these universes could bubble into existence, collide, or even evolve over time. The constants we take for granted, like the speed of light or the charge of an electron, might be frozen accidents, the result of how our universe's higher dimensional geometry settled into place. Critics argue that this idea is untestable, a philosophical leap rather than hard science. Yet supporters counter that the sheer mathematical elegance of string theory, combined with its ability to unify physics, makes it too compelling to ignore. Whether the string landscape is real or not, it forces us to confront a humbling question. Is our universe's shape just one page in an infinite cosmic library? And if so, what other breathtaking geometries might be out there waiting to be discovered? Now, let's twist our perspective even further with a theory that bends not just space but time itself. Imagine a universe shaped like a donut where time doesn't just march forward, it loops back on itself. This is the Toroidal Universe, a place where closed time-like curves could allow events to circle back, blurring the line between cause and effect. In this bizarre cosmic model, time isn't a straight arrow but a coiled ring. Picture traveling far enough in one direction and eventually returning to your own past like a cosmic déjà vu. This idea emerges from the math of general relativity, where extreme curvature in spacetime, like the kind you'd find in a toroidal universe, could create paths where time folds back on itself. But here's the catch: if time loops, what happens to causality? The very foundation of reality relies on causes preceding effects. If you could go back and, say, prevent your own birth, the paradoxes pile up fast. Some physicists argue these loops are mathematically possible but physically forbidden by quantum mechanics or other unseen laws. Others suggest nature might find clever ways to avoid paradoxes, like allowing only self-consistent loops where events align perfectly to avoid contradictions. The Toroidal Universe isn't just a sci-fi trope, it's a serious challenge to how we understand time's flow. Could the arrow of time be an illusion, a side effect of our universe's shape? Or are these closed loops a hint that time is more flexible than we ever imagined? Whether real or not, this theory forces us to rethink one of the most fundamental aspects of existence, the unshakable direction of time itself. Now, let's zoom way in, to the very fabric of reality itself. At scales so tiny they defy imagination, spacetime might not be smooth and continuous, but a bubbling, turbulent sea known as quantum foam. Picture the surface of a boiling pot, constantly churning with fleeting bubbles that pop in and out of existence. That's the essence of the quantum foam universe, where the smooth spacetime we're used to dissolves into a chaotic dance of microscopic fluctuations. This wild idea comes from combining quantum mechanics with general relativity, two pillars of physics that don't always play nice. At the Planck scale, a distance so small it's a trillion times tinier than an atom. Spacetime itself could be frothing with tiny wormholes, virtual particles, and fleeting distortions. These aren't just mathematical quirks, they're a fundamental feature of reality at its most basic level. But here's the twist: if spacetime is foamy at the smallest scales, what does that mean for the universe as a whole? Some theories suggest these quantum fluctuations could leave faint imprints on light traveling across the cosmos, subtly altering its path or energy. Others propose that foaminess might explain why gravity seems so weak compared to other forces. It's diluted by the chaotic structure of spacetime itself. The quantum foam model challenges our intuition about the very nature of reality. Is the universe's large-scale smoothness just an illusion, an average of countless microscopic storms? Or could this foaminess hint at a deeper layer of physics, where spacetime itself is stitched together from something even more fundamental? While we can't yet observe these Planck-scale frenzies directly, the quantum foam universe reminds us that the cosmos might be far stranger and more turbulent than it appears. Now, let's take a step into a universe where reality isn't just three-dimensional, it's a cosmic hologram, but with a twist. Imagine a world where the entire universe is like a holographic projection, but instead of being smooth, it's built like a fractal, repeating intricate patterns at every scale. This is the holographic fractal universe, a mind-bending blend of two revolutionary ideas, the holographic principle and fractal geometry. The holographic principle suggests that all the information in our three-dimensional universe might actually be encoded on a two-dimensional surface like a cosmic DVD. But here's where it gets even wilder. What if that encoded information isn't just flat and uniform? What if it's structured like a fractal, with self-similar patterns repeating infinitely, from the largest galaxies down to the tiniest particles? Picture a snowflake's intricate design, but applied to the very fabric of spacetime itself. Cutting-edge research in quantum gravity is exploring this possibility, asking whether the universe's underlying code might be fractal in nature. Some scientists propose that black holes, often considered the ultimate information encoders, could hold clues. If their event horizons store data in a fractal-like way, it might mean the entire cosmos operates on similar principles. Others are investigating how this could explain the strange, large-scale structures of the universe, like the way galaxies cluster in patterns that eerily resemble fractal networks. The implications are staggering. If the universe is both holographic and fractal, it could mean that reality is far more interconnected than we ever imagined. Every part might contain the whole, like a single leaf reflecting the structure of the entire tree. While this idea is still on the frontier of physics, it challenges us to rethink not just the shape of the universe, but the very nature of existence. Is our cosmos a vast, shimmering hologram woven from fractal threads? The answer might lie where quantum gravity meets the geometry of the infinite. Now, let's shift our gaze to a different kind of cosmic blueprint, one where the universe isn't perfectly uniform in every direction. Enter the Bianchi models, a fascinating set of solutions to Einstein's equations that describe universes which are homogeneous, meaning they look the same at every point, but anisotropic, meaning they don't look the same in every direction. Imagine a loaf of bread where the slices are identical in composition but stretched or compressed differently along each axis. This is the essence of a Bianchi universe. These models are named after the Italian mathematician Luigi Bianchi, who classified the possible types of such spaces way back in the late 19th century. While most cosmological models assume isotropy, the idea that the universe looks the same no matter which way you look, the Bianchi models challenge this by allowing for subtle directional differences. This could help explain some of the irregularities we've observed in the cosmic microwave background, those faint echoes of the Big Bang that carry hints about the universe's infancy. For instance, certain anomalies, like the so-called axis of evil, a mysterious alignment of temperature fluctuations in the CMB, might find an explanation within these anisotropic frameworks. If the early universe wasn't perfectly smooth in all directions, it could have left behind imprints that still linger today. Some researchers even speculate that a Bianchi-type universe might reconcile discrepancies in measurements of the Hubble constant, the rate at which the cosmos is expanding. Of course, the idea isn't without controversy. The standard cosmological model has been incredibly successful, and introducing anisotropy adds complexity. But science thrives on testing boundaries, and the Bianchi models remind us that the universe might be more textured, more nuanced than we've assumed. Could the cosmos have a preferred direction, a hidden grain like wood, shaping its expansion in ways we're only beginning to detect? The answer might lie in these elegant, century-old equations, waiting to reveal deeper truths about the shape of reality. Now, let's turn our attention to a concept that feels like it's straight out of science fiction, yet might hold the key to one of cosmology's biggest mysteries. Picture a universe just like ours, but flipped, where the rules of physics are mirrored in unexpected ways. This is the idea behind the mirror symmetry universe, a theory rooted in the elegant mathematics of string theory. String theory suggests that at the most fundamental level, the universe is made up of tiny, vibrating strings. One of its most intriguing predictions is mirror symmetry, the possibility that two seemingly different universes could actually be geometric reflections of one another. In this scenario, our universe might have a hidden twin where certain physical properties, like particle charges or even the direction of time, are inverted. What makes this idea especially compelling is its potential to explain dark matter, the invisible substance that makes up most of the universe's mass but eludes direct detection. If dark matter particles are mirror versions of ordinary matter, interacting only weakly with our familiar world, they could account for the gravitational effects we observe without being seen. Imagine a shadow universe perfectly aligned with ours yet just out of reach, its presence felt only through its gravitational pull. Some physicists speculate that mirror symmetry could also resolve other puzzles, like why the universe has more matter than antimatter. If the mirror universe favors antimatter, for example, the imbalance in our own cosmos might make sense. Of course, this remains speculative. No direct evidence of a mirror universe exists yet. But experiments searching for faint interactions between ordinary and mirror particles could one day test the idea. The beauty of this theory lies in its boldness. It challenges us to rethink not just the shape of the cosmos, but the very nature of reality. Could the universe we know be just one half of a grander, symmetrical whole? As we peel back the layers of string theory's equations, the answer might be hiding in plain sight, reflected in a mirror we've yet to fully glimpse. Now, let's shift our gaze to a theory that turns the cosmos into a grand cosmic detective story. Imagine the universe not as a smooth expanse, but as a vast, intricate crystal where galaxies align in repeating patterns, revealing its hidden shape. This is the cosmic crystallography hypothesis, a bold idea that suggests the universe's geometry might be encoded in the way galaxies are scattered across space. Think of it like this: if the universe were finite and had a specific topology, say a donut shape or a twisted loop, light traveling through it could wrap around and create duplicate images of the same galaxies. Astronomers call these ghost images, and spotting them would be like finding fingerprints of the universe's true form. It's similar to how a crystal's atomic structure repeats in a predictable lattice, except here, the lattice is made of galaxy clusters stretching across billions of light years. Researchers have scoured sky surveys for these telltale repetitions, searching for identical circles in the cosmic microwave background or matching galaxy patterns in opposite corners of the sky. So far, the evidence is elusive, but the hunt continues. If proven, this hypothesis could answer one of cosmology's oldest questions: is the universe infinite, or does it fold back on itself in some exotic geometric way? What's fascinating is how this idea bridges the very large and the very small. Just as crystallography reveals the hidden structure of minerals, cosmic crystallography could unveil the architecture of the cosmos itself. It's a reminder that sometimes the universe's grandest secrets are hidden in the patterns we've yet to recognize, waiting for us to connect the dots. Now, let's explore a theory that turns the very fabric of reality into a cosmic balancing act. Picture a universe where everything, every star, every galaxy, even the energy of empty space adds up to nothing. That's the mind-bending premise of the null universe hypothesis. At its core, this idea suggests that the universe's total energy is precisely zero, with the negative pull of gravity perfectly cancelling out all the positive energy from matter and radiation. Think of it like a cosmic ledger where the books always balance. The gravitational energy of the universe acts like a kind of debt, offsetting the credit of mass and energy. It's a concept that emerges from Einstein's equations, where the curvature of space-time and the energy within it can mathematically zero out. This isn't just a quirky calculation, it has profound implications. If true, it could mean the universe literally came from nothing, requiring no external source or creator to explain its existence. Philosophers love this idea because it sidesteps the age-old question, why is there something rather than nothing? If the universe is a perfect zero, then nothingness and existence become two sides of the same coin. Meanwhile, physicists are drawn to its elegance. A null universe fits neatly into theories of quantum fluctuations, where particles pop in and out of existence spontaneously, as if the cosmos is borrowing energy from itself and repaying it instantly. But here's the twist: even if the universe's energy sums to zero, it doesn't feel like nothing. We're here, after all, experiencing a reality filled with galaxies, black holes, and coffee cups. That's the magic of this theory. It suggests that everything we see and touch might just be an intricate dance of positive and negative values, a cosmic illusion of substance emerging from perfect equilibrium. So the next time you gaze at the night sky, remember, you might be looking at the ultimate free lunch, a universe that, in the grandest accounting, costs absolutely nothing. Now, let's stretch our imaginations to the absolute limit with a theory that redefines reality itself. This is the ultimate ensemble, Max Tegmark's mathematical universe hypothesis, where every possible structure that can exist mathematically does exist as a physical reality. Think of it as the grandest multiverse of all, one where the cosmos isn't just a single entity but an infinite collection of every conceivable universe, each governed by its own set of mathematical rules. Tegmark's idea starts with a simple but radical premise. Mathematics isn't just a tool to describe the universe, it is the universe. In other words, if a structure or equation can exist mathematically, there's a physical reality somewhere that corresponds to it. This means universes with different dimensions, alternate laws of physics, or even entirely unfamiliar forms of matter aren't just theoretical, they are out there, existing alongside ours in an unimaginably vast ensemble. What makes this hypothesis so compelling is how it sidesteps the fine-tuning problem. Our universe's constants, like the strength of gravity or the mass of an electron, seem perfectly calibrated for life. But in Tegmark's framework, every possible combination of constants exists somewhere, and we simply inhabit the slice of reality where conditions allow us to exist. It's like winning the cosmic lottery, except every possible outcome happens in some universe. Critics argue that this idea borders on metaphysics, but Tegmark counters that it's a natural extension of physics' reliance on math. After all, equations predict phenomena from black holes to quantum particles with uncanny accuracy. If math describes reality so perfectly, why couldn't reality be math? The implications are staggering. It suggests that every story, every alternate history, every fictional world you've ever imagined might exist in some mathematical form, not as simulations but as genuine physical realities. So where does that leave us? In a cosmos where the boundaries between science and philosophy blur, where the answer to "why is our universe this way?" might simply be because every possible universe is out there. It's a humbling, exhilarating thought, one that turns the night sky into just one page of an infinite cosmic library. And with that, we've reached the edge of what cosmology can even speculate about, for now. And so, we've journeyed through 30 extraordinary theories about the universe's true shape, each one stretching the limits of our imagination and reshaping how we see reality. From the flat universe we measure to the holographic cosmos that might be a projection, from the donut-shaped torus to the infinite mathematical multiverse, every idea challenges us to rethink what's possible. Some theories fit neatly into our current understanding of physics, while others push us into realms where science and philosophy collide. What's remarkable is how each of these perspectives offers a unique lens on existence. Maybe you're drawn to the elegance of a spherical universe, where space loops back on itself, or perhaps the holographic principle's mind-bending implications feel closer to the truth. Or maybe Max Tegmark's mathematical universe resonates with you, the idea that every possible reality exists somewhere in the grand cosmic library. Now, we'd love to hear from you. Which of these theories feels the most compelling? Do you think our universe is flat, curved, or something even stranger? Drop your thoughts in the comments below. Let's keep the conversation going. And if you're hungry for more cosmic mysteries, don't forget to hit that subscribe button and ring the notification bell. The universe is full of secrets waiting to be uncovered, and we'll be here to explore them with you. Until next time, keep looking up and keep wondering.